Hello everyone. So any questions before we move forward?
Yeah, I had a question about the price equation.
Yeah, sure. Yes. This is who is
So
this? Sean.
it's
Okay.
Sean. Yeah.
Yes. Yes.
So
Yes.
the way we derive the price equation, it applies to alleles, right?
It applies. It applies to any heritable trait.
Any heritable. So
Yeah.
I was just thinking about whether you can apply the price equation to something like community ecology, where you think about the trait as a species identity. Would the assumption still hold?
Yes, I think it should hold. So anything that has any set of entities, it could be, you could do it at the level of species, you could do it at the level of groups, you could do it at the level of individuals, you could do it at any level as long as there is something that's heritable from one generation to the next generation. You can use this equation. Okay. Absolutely fine. There is no problem at all. Yeah.
Sir, the third year UGs have an interaction session with like Anil Kumar today at 4:30. So can we leave by then?
Absolutely fine. Yeah. I mean, I understand that, there are, I mean, I wanted to email all the third year students, but I didn't have time at all. I was like busy with, sort of lots of meetings since morning, including one with Anil Kumar. And so, yeah, totally fine. Absolutely fine. No problem at all.
Thank you.
So in fact, most likely, I may not ask for any sort of, assignment today. So, because of this reason, so I will just cover some topics. Those who can stay can sort of just think through a small problem and go. But if you need to leave early, no problem at all. Okay. So any other questions? Okay. So are you able to see this now? It's not connected. 1 second. The Bluetooth is not on. 1 second, please. Oh, now it's working. Okay. So today we will do another very interesting scenario known as cooperation. Cooperation between organisms. So what do you usually understand by the word cooperation?
Symbiotic relationship.
That's just another word. So something can describe it a bit more.
Helping
it's two.
Yeah, please.
It's two-way.
What is two-way?
So an interaction where both the parties sort of are mutually benefited.
Mutually benefit, yes.
Okay, okay. Mutual benefits. Okay. So it's an interaction where both the parties benefit mutually, right? Okay. Anything
there is
else?
a cost as well. Cost to
And
cooperation.
there is a cost.
Both suffer a cost.
Okay. Okay. It's a type of interaction. Can somebody give an example of cooperation?
The cattle egret and the ticks it eats on buffaloes, cattle, etc.
So that usually we don't call cooperation. That's yeah. So cooperation, okay. Maybe we can start by sort of narrowing the definition. So those are cases of maybe mutualism or symbiosis. So usually when we say cooperation, we sort of think of within species interactions. So that's one way to distinguish cooperation with, let's say, symbiosis or mutualism.
Raising a call for predator, I mean, the monkeys on top of this thing, I mean.
Yeah, that's absolutely. Alarm calls are an example of cooperation. Why is it an act of cooperation?
So
Can you
because,
define these things? What are the mutual benefits and what are the costs?
yeah, cost is that, I mean, it may get the attention of the predator because it is raising the alarm. So it may get attention of the predator. Yeah, higher risk.
So risk of predation, right? Okay.
Yeah. So, so the entire troop is benefited by the alarm call.
Benefit. To the troop. Basically other individuals, right? What else? Any other examples?
Hunting as a pack.
Group hunting. So what is the cost?
The amount of food you get for yourself might be lower, but the benefit would be
Sharing the
that
resources, right?
Right. And the benefit would be that maybe your rate of hunting success would go higher.
Benefit. Higher rate of hunting. Okay, excellent. Anything else? Okay, I think these two are actually good examples. Okay. Do you think these two examples belong to the same category or there's something subtly different between these two examples?
There is a difference, I think. In alarm calls, I mean, not just intra-specific, others also get benefited. But I think.
Okay, let's just focus in this case on benefits to the within species only. So let's not worry about somebody else getting benefited in the process. Okay. So let's think of only the conspecific benefits.
So in group hunting, everyone sort of gets an equal amount of benefit, while in alarm calls, the one who's giving the alarm is putting itself at a much higher risk than others are. So the benefit the caller receives is comparatively lesser because it's putting itself at risk compared to who the call is supposed to be for. While in group hunting, everybody sort of gets benefited equally.
Right? Yeah, that's a very good point. So in group hunting, the costs are borne by everybody. Okay, right? And so are the benefits. Right? But what about the alarm call? Who pays the cost?
That individual who is giving the call.
The caller pays the cost. Who gets the benefit?
The entire troop.
And will the caller get any benefit?
It depends on how we define benefit. Because
True.
here, because it's looking at the predator and it's giving the call, it's actually aware of the predator and can survive better than the others.
How though? I mean, is it just better to just hide immediately? Why give a call at all? I would hide better anyway, because I have seen, if I'm the individual who is deciding whether to call or not, I have seen the predator, I will just hide. So the question here is about the calling part, right? How did calling help me? Does calling help me hide better?
No, I think the benefit comes from saving your family members because they also
Let's
have.
think of the selfish benefits only.
It's like
Okay.
some individual at one
Yes,
point
because
they
he
get
is
a
the
call
first to
and then
identify. He will have a lead time in to escape.
like this call giving may be distributed among the individuals, right? So it's not like only a particular individual is going to give a call. It's like at one point of time.
Yeah.
At one point of time, one individual may give a call, and then later on, some other individual may give a call.
They take turns.
Yeah. Beside about group hunting, I'm not sure if this one the benefits are shared equally because there may be and the costs too because there may be few leaders of the pack, right, who may be more efficient at hunting and things like that. So
Okay.
in such a situation,
Yeah, true. That's also possible. It's possible that there are some leaders who are better hunters. There are, babies who don't. So basically, well, let's make a life a bit easy, like we always do in all these models, which is, let's assume that everybody is equal in every aspect. Okay, let's assume homogeneous set of individuals. Okay, let's make a few assumptions when understanding this. One is that, let's assume homogeneity in all other aspects. Okay. Example, no leaders, right? Or experienced individuals. Okay. Let's assume another very crucial thing for the time being. Let's assume one-time interaction. Do you understand what this means? This is a so think of scenarios, two types of different scenarios. Okay, let's say the example of troop we considered. There are two possibilities. A troop always stays cohesive, like let's say baboon troop. Okay, they're always same sort of extended maternal family. And in that case, the interactions happen repeatedly. There are hierarchies among individuals. Okay, and there might be some leaders and there might be some more experienced individuals. There is a age hierarchy as well and so on. But the other extreme, those are typically found in many primate groups. Now let's think of other type of groups. For example, types of groups where they don't stay cohesive together among the same members all the time. Okay. For example, think of elephant groups. So although there is some hierarchy between individuals there, for example, there's always a matriarch in an elephant group, but they don't always stay together. They also merge and split. So those are called fission-fusion groups. Okay. In such a group, it might be difficult to expect that they are taking turns because every time this scenario happens, they may actually be in very different groups. Okay. It may also be applicable to many other species where the groups don't stay together as a family or as some kind of a unit, but they sort of frequently go merge and split with one another. Okay, so or another, if you want to think in a context, imagine there is a one-time event that happens. Okay, not a repeated event, but a one-time event where there are two individuals. One has detected their predator, the other hasn't. The question is, should you now call or not call? Okay, what circumstances should lead to calling and what circumstances should not lead to calling? That's another way of thinking. Okay, so let's assume this, what is called one-time interaction. So the opposite of this would be called, this is also called, non-iterative strategies, and the opposite of which will be what are called iterated strategies, things that happen repeatedly. We'll also study them if we have time. Okay, so for the time being, to sort of make sense of the principles, let's stick to these two assumptions. Is that fine? Now, with these two assumptions, based on what all you have said something very interesting that, in the context of alarm calls, so in the cost is paid by the caller, but the benefit goes to everybody else. Is that right? On the other hand, in the case of group hunting, benefit and cost both are sort of equally shared. So there is this very simple, interesting, but fundamental difference between these two scenarios. But you're right that the real world is more complex, and we can modify these rules to accommodate those. Okay, to start with, let's just make the simple assumption. Let's now write down what we call, whenever we have these kind of animal strategies, what do? We define the strategies like we did for hawks and doves. And then what do we do after that? We define the payoffs, right? So can we now define strategies? Okay. Okay, let's think of, so these are broadly called cooperative strategies. Okay. And there are basically two types of cooperative strategies. Okay. Either you cooperate, alternative is you defect. Okay, so let us denote cooperate by C and defect by D. Okay. So now that we have defined two strategies, let us say how the two strategies may interact via this payoff matrix. Okay. So here I'm going in the column, I'm going to write the focal individual, and in the row I'm going to write, sorry, in the rows I'm going to write focal individuals, and in the column I'm going to write the other individual. Okay, C and D. Okay, sorry about this. Okay, so what happens when two cooperators interact?
They get the same benefits.
So they both get the benefit, B, let's call that B, but they both pay the cost. Okay, let's call it C. Now, what happens when a cooperator interacts with the defector? So you abstract, just at this stage you have to now abstract whatever we have written about to this simple broader strategy is called cooperation and defection. What happens when a cooperator interacts with a defector?
Minus C.
Okay. Why is that? Because cooperator and defectors meet, and when that happens, cooperator has paid the cost. Okay, but does the cooperator get a benefit?
No.
Yours in this, the way you have said, no. So I'm happy to keep it that way, minus C. Okay. So in the same cooperator defector, what happens to the defector? What does defector get in the interaction? Defector gets all the benefits. Okay. So in this interaction, when cooperators and defectors meet, defectors get the benefit, cooperators get the cost. Okay. What happens when defectors and defectors meet?
Nothing.
Nothing happens. So it means they got basically, they
Zero.
neither cooperate, nor do they pay cost, so it's basically zero. Is that fine? Okay. So this form of cooperation which we just wrote down is also called altruism, or strong form of cooperation. Okay. So now, if something is strong, there must be some weaker version also, right? What can you guess? What could be that? So let's write down. So let's think of a weaker version. How do you think this looks like.
There's no cost to or to cooperating.
Okay, before we do that, whatever we have written, does this match more with group hunting, or does this match more with alarm calling?
Group hunting.
Sorry.
No,
So whatever we have written looks more like group hunting.
Maybe like alarm calling, right?
Alarm calling. Alarm calling.
I
Alarm
think it's
calling.
alarm calling.
Yeah, so alarm calling. Why so? Because in the CD interaction, right, cooperator defector, the cooperator got nothing in return, right? That's really the classic case of a alarm call. The alarm caller has a higher risk of predation, but which is denoted with -C, but actually got nothing. Okay, only when in this mutual, then both of them are callers. If you think of them as probabilistically, sometimes you are the recipient of the benefit, sometimes you are the caller, right? So in such a case, you can write B minus C. Okay. So I will lose this bit. Okay. So
I'll talk to you later.
okay. So so this is actually more like alarm calling. Okay. How about, so why is this not group hunting?
The entire cost is borne by the cooperator.
One person, right? Whereas in a group hunting scenario, let's say there's a defector who doesn't participate in the hunting process, but comes to eat. So even in that case, the hunter, the participant in the hunting will still get some food. The food is still shared. It is not that the hunter only paid the cost of hunting, but the hunter also had some benefit in the end. So there is, so that's the difference. So if you now, can we account for that and write somehow this what could be a weak cooperation?
You have only costs.
So basically in the weak cooperation, you do get some benefit. The benefits are shared. You are paying the cost, but you do get the benefit. Okay. And in this DC interaction, the defector doesn't get the full benefit, but only get half of it because they actually share the benefits. Okay. And in the DD, of course, is always 0. And what about CC? CC need not change at all. It could just be B minus C. Okay.
Wouldn't it be
maybe one can think of sorry,
B by 2 minus C, because everywhere else you've done B by 2 because you've shared, right?
Then the C also gets by 2, no? Both of them are shared, right? Because both of them are participating. So we can just make it half for both. Huh?
Okay.
Yeah. So this is called a weak form of cooperation. Okay. So one can think of more examples also in a human life context. Imagine there is this example called snowdrift. Snowdrift game. So what happens? Imagine you are riding your vehicle in a Himalayan landscape, and there is a section of road where a massive glacier has just fallen. Okay, and you are here, and there is somebody there. Now the question is, who will clean up this mess? Okay, what do you think is a better payoff matrix for this? Should you, so if both of them clean up the mess, they are both cooperators, right? If you don't, the other person doesn't, the other person becomes defector and you are the cooperator, and vice versa, right? So which payoff matrix fits this scenario better?
The weak cooperation.
The weak form, right? Okay. Yeah. So because even if the other person doesn't cooperate, you clean up, you still get the benefit of being able to cross the road. Of course, you paid a lot of costs in terms of time and effort, but you still get to cross the road. Okay. So this would be a weak form of cooperation again.
So shouldn't B minus C itself, because here it may this means that the corporate with corporate will have a lesser
yeah. So you're right.
than,
Basically, whether the benefit is whether the resources are shared in the sense of if it's a consumable resource, you will have a factor of half, like one we did in the previous case, like hunting. But if it's not a consumable resource, like when you open the road space, I mean, you can't consume a road space, right? It's there. So in that case, you don't have to divide by half. Okay.
no, sir, but here, like if you're using the same definition, a CC interaction gives a lesser value than CD interaction for C. And that doesn't make sense, right?
Say that again, sorry.
Like a CC interaction gives a lesser net result than CD interaction.
In the snowdrift game.
Yeah.
It's possible, so that's why, I'm saying, if you have to classify either as a strong case or a weak case, what one will you do? I'm not, I'm saying, I'm meaning it to say that the payoff matrix will be identical. I'm just going to say, I'm using that word to mean which class of the cooperation does it belong to. The payoff matrix, I agree, will be different, and you're also right that the CC corp will, no, but the cost will be shared. No, it will be, benefit will be same for both B minus C by 2, right? In this snowdrift. If you want to quickly write this down for snowdrift, how would this look like?
So I'm just talking about the two terms in the weak form of cooperation itself.
Here is it?
Yeah, the CC interaction, CD interaction. The CC interaction can't have a lesser net result than CD interaction, right?
Why not?
Because like when two cooperators work, you will have a higher net result, total net result, right? Then
why?
Because there's higher, like lesser effort put by each individual.
So you're assuming some kind of a multiplicative factor, huh? That doesn't always have to happen, by the way. It can happen. It's not guaranteed. For example, if there's a nonlinear response, then you're right. Okay. But it's not guaranteed though. So in this simple game, it does not happen. But you can construct other cases. For example, think of the example of quorum sensing in bacteria. So what happens is, the net effect of multiple individuals doing the same thing there, which is the quorum sensing, has more effect than sum of all the individuals. So, but it's not always true. It doesn't have to be always true in all the cooperation games. Is it clear?
I had a question. Can we say that for just weak cooperation, the benefits and costs for both cooperators and defectors are much lesser than in the strong cooperation? Is that a valid statement?
So, see, I will tell you what is the fundamentally distinguishing factor between weak and strong. In the strong form, okay, or what's also called altruism, I think this altruism is a key word there. Okay, there is no self-benefit. To cooperators. So the benefit only comes from other party. So here when the CC happened, the benefit came from the other individual, this benefit, but the cost was the focal individual's cost. And the CD, whatever you do doesn't come back to you. Okay. So in some sense, like the alarm call has literally no benefit to you in that interaction. It only has a cost component. Okay. Likewise, when honeybee goes and feeds, a sterile honeybee goes and feeds the babies, literally there's no cost to the individual. There is no benefit to the individual actually doing this. Okay. So that's the fundamental difference between strong and weak forms. Now, the exact order of how the payoffs change, and depending on that, there are many different sort of, strategies that people have labeled and so on. But if you ask me, I would say the fundamental difference between altruism and other forms of cooperation. So much so that usually people don't even call the first one I have written. People usually don't use the word cooperation for the one above. They usually use this to mean altruism, and this is what when they mean cooperation. So altruism is the case when there is no self-benefit. Cooperation, by usually when you see the word cooperation, you assume that it is a weak form of cooperation where there is self-benefit. Is that distinction clear now? If you see it in this simple way, you will see that Snowdrift also has a self-benefit. Okay, coherent sensing has self-benefit, right?
So could we say something like in the first altruistic case, the benefit is less than the cost, but in the self-benefit case, the benefit is greater than the cost paid?
Are you saying that in altruism, B has to be less than C?
Seems like it with all the examples you've given.
No, it doesn't have to be. Why? No, it doesn't have to be. So, you just think of the following, right? Benefit. So you're right. That's. I mean, it's possible that in some real cases that's indeed the case. And if it is indeed the case that B is less than C, then we can see what is the ESS. If not, we can see what is the ESS. But if you want such a behavior to persist, as we will see in the calculations, B will of course have to be greater than C. Okay. So now, if all the questions clear, if you have more questions, yes, please. Yeah.
Sir, in the weak form of cooperation, can you explain why in the C and C interaction we have half the B minus?
So it really depends on what is the sort of payoff you're thinking of. Imagine if it is a like a hunting resource, right? A prey that you have caught, right? If B is the value of your prey, you only get B by 2 because there are 2 individuals now, right? Likewise, the cost you had to pay was half of it.
So C is in itself the cost of sharing, right? So why
So
have
the way I have written here is C is the time to capture, maybe.
Okay, so the
probability
cost of
capturing, cost of hunting, yes, and then the benefit is the hunt itself, the prey.
Right. So
in that case, you pay. I'm assuming that if there are 2 of you, take half the time, and then you also get half the resource. Okay.
In altruism, in the C and C, we have written B minus C. And if I remember, we were talking about alarm calling. So if I'm assuming that there's at sometimes I am the one who's calling and sometimes I'm the benefactor, then shouldn't it be the half of B minus C?
Yeah, true. So if you want to model exactly for alarm calling, you're right, but I'm not doing it that way. So that was an inspiration. So you should now think of it as slightly more abstract, form. So which is why, in fact, if I'm right, so as I said, the factors of half and all, but they will really depend on what exactly the scenario you're modeling. Okay, so don't worry too much about those factors, at least in this stage. So even, for example, if you remember, even in the hot dog game, so one of you suggested there must be a half, the other suggested there's no need for a half, and both of you are right for the context that you were saying. So in fact, the mixed strategy equilibrium we got has a factor of half more than classic textbook answers. Okay, so as long as you justify the scenario you are doing and then you're writing your payoff matrices, it's totally fine. But the key distinction between the 2 scenarios is that of difference in the self-benefit.
Right.
And another example of, before I forget, I just want to mention, this is also, there are another two important names, the altruism payoff matrix is also called prisoner's dilemma. Have you heard of this? So this maps exactly with the prisoner's dilemma payoff matrix. This actually doesn't quite, but usually because of the various halves you have written at various places. But usually if you write it, one of the classic examples of the cooperation is that of public goods gain. Do all of you understand what are public goods? So for example, think of grazing commons. So it's a public good or a park, right? So if I invest my time in cleaning a park, I'm investing some time, I also get the benefit. But the one who doesn't invest time still gets the benefit. Okay. But is not paying the cost. Okay. So those are the examples of public goods. Like again, even the snowdrift game, right? Clearing the road will help everyone, but the cost is paid by those who are actually cooperating. Okay. Okay. So yeah, somebody had a question. Sorry.
No, I was just thinking when we said no self-benefit, it was slightly counterintuitive in the first case when you have B minus C. But now that you're telling that that's also the prisoner's dilemma payoff, I might have to think about it a little more.
So why is there a B if there's no self-benefit? Is it your question? So this benefit is coming from this cooperator.
But for the focal individual at any point in time or any instance, you shouldn't have any benefit, right? If it's altruism.
That's not true. That's not true. I mean, it doesn't have to be true that way,
So some indirect form of benefit without actually getting it.
Well, I mean, so yeah, there is. How do I mean, your question is valid. I'm thinking how to explain that better. So when we say no self-benefit, we mean that the action of your cooperation does not give you the benefit, but the action of somebody else's cooperation will benefit you. Does it make sense? That's the way self-benefit is defined.
I see.
So self-benefit is when you are the cooperator. If somebody has raised their hand. Eli?
Yes, I had a doubt. I had read previously that altruism, that an animal, like not an animal shows a different degree of altruism based on how the other animal, how close the animal is related to him.
So we'll come to that. We'll come to that. So far we have made no assumptions about who are these individuals, right? Okay, so we will come to that. That's a very good point. We'll come to that. Okay. Okay. So shall we move on now? Is it okay? Okay. Now you already know how to analyze ESS without having to write down complicated payoff matrix equations, right? How do you do it? You know how to identify pure strategies. Is that right? So let's focus on prisoner's dilemma. Okay. I will leave it as an exercise for you to do the weak form of cooperation. Okay, so let's look at prisoner's dilemma. So how do we analyze this? So remember, if the first thing to look for always is pure strategies. If pure strategies are cannot be invaded, you have found an ESS, right? So let's look at the pure strategy of CC. We start here. What do you now do? Basically, the pure strategy has a payoff of B minus C. Okay. Now, you ask the question, if you now switch to D, what happens? You get B. Okay. So you have switched from, let's say in the CC, if the focal individual switches from being a cooperator to being a defector, right? What does the payoff increase or decrease? The payoff has increased now, right? B minus C to B is an increment. So therefore, pure cooperation strategy, are also called altruism, is not an ESS. Do you agree with that? Altruism is not ESS. Okay, because switching to defector is always better than continuing as a cooperator. Now, the next thing you will do is, what if both of them are defectors. Now, if the defector switches to C, what happens? Does the payoff increase or decrease?
Increase.
It decreases. Should you do it? No, right? So therefore, stay where you are, which means D is NESS, which basically means that in this simple prisoner's dilemma scenario, defection is basically the ESS. Any questions on this? Which means altruism is not stable. Altruism basically cannot happen. Any questions?
If it's unstable, then why do we still observe
Why does it exist?
Why does it exist? Okay, that's what we should. That's precisely the point of today's class. Why does it exist? So, in fact, not today's. This is precisely what has puzzled people since Darwin. Now, why should altruism exist if it's not an ESS? But remember, we made an assumption. We have made obviously some assumptions in the process of writing these, right? So if we now try to disentangle the assumptions, there was one very important assumption we made, okay, when we wrote down the payoffs or the fitness. Let's see if I can find that. In fact, somebody actually asked me, actually told this last time. Not in the last class, I think. I think it was in the one before. When we were writing when we did the hug dove. Okay, let's see if so we wrote down hug dove, right? We wrote down the payoff. Okay, here I was just telling how to look at payoff matrices, right? So we wrote down, when we did the hug dove, we did this payoff matrix, we did all these calculations, right? Okay, so there is somewhere I have written, if you now notice, an assumption. Of course, we made a number of assumptions. I'm not saying it's the only assumptions we made, but there is one key assumption that is relevant now for us, which is interactions between animals is random. When did we make this assumption? When we wrote down these two payoffs for the hawk and dove. And of course, in the corresponding case that we are discussing today, it will be the assumption that we do when we calculate the payoffs for cooperators and defectors. Where was this assumption about randomness made? When we wrote down the fact that what is the probability, given that you have a hawk, what's the probability that he or she will interact with another hawk, right? That was basically proportional to the hawk frequency. That's what we assume, right? That requires that, the fact that we just wrote P here requires the assumption that the interactions are random between individuals. Is it clear? So you can somehow maybe relax this assumption. Maybe we'll find a way to make sure altruism doesn't die. Okay, so that's the premise today. And let's do basically now these type of calculations to see how we can make sure the altruism doesn't die. Is the idea clear? Okay, so even if it's not clear, when we do the calculations now, it will be clear. Okay, so remember the basic idea. How did we really we were able to look at column-wise comparisons in the payoff matrix. That was true only when the interactions between organisms were random. Okay, at the moment that is, if we want to relax that assumption, we will have to actually write down clearly this payoffs for the okay, so let me just make a new notation now. Let's call A is equal to all time altruistic behavior. Okay, and let's denote D to mean all-time defection. Okay. With that definition, I have actually changed from C to A. Sorry. Let's just stick to C. All-time altruistic behavior, and D is all-time defection. Is that fine? So now we want to write down the payoff of the C. Okay, so I'm going to ignore this baseline fitness business because we know it just gets cancelled anyway. I'm also going to skip that coefficient test because it's again going to get cancelled anyway in that. So omega C, which is the fitness of cooperator, is given by this probability that of interaction with another C, right, times the payoff to C when you interact with C, plus probability of interaction with D times V C D. So I'm using the same sort of notations as I did previously. Let us also write this in terms of probability that given that you are a C, you're interacting with a C, I'm writing that as PCC. Okay. Given that you are a C, what is the chance that you interact with D? And then having done that, what is the payoffs to cooperator in interaction with D? And now this is a very complicated set of notations. So let me just make sure you all understand this and you also don't get confused. Okay. Probability of a given C interacts with C. VCC probability. Oh, should I just do it in a more general way? Oh, otherwise I'll have to write 4 different things. Okay. Just do it in a very general. Sorry. Okay. Probability of A comma B means that probability that a given B interacts with A. V A of B means payoff to A in interaction with B. Is that fine? Please make sure you all understand these notations. Any questions? Okay, so if there are no questions, I will move forward. So we know this is omega C. Now let's just simplify it now. What is VCD? What is the payoff to cooperator when you interact with a defector? It's just 0, right? Okay. What is the payoff of cooperator interaction? That will be B minus C. Is that fine? So basically, therefore, we have omega of C is equal to, omega of C is equal to probability of cooperators interacting with cooperators. Sorry, I should be very clear. Probability of a given cooperator interacting with a cooperator times B minus C. Okay. Now, likewise, let's write this equation number 1. Now, what is omega of D? It will be probability of a given defector interacting with the cooperator times the associated payoff plus probability of a given defector interacting with defector. Oh, by the way, this is not 0, right? I hope
This is minus
this
C.
is minus C, no?
sir.
Yeah. Why did nobody wake me up? This is minus C. Okay, so that means there is additional term here, no? This is minus of C times P of, okay, V of dt, right? I noticed that only when I was writing this, okay, this is the one that's actually 0, 1. V dt is 0, okay? And what is VDC? This is B, right? Okay, so therefore we have this is equal to probability of a defector meeting a cooperator times B. Is it fine? Okay, so what is the condition under which now cooperators will win over defectors?
Omega C greater than omega D.
Did we call them cooperators or altruists? I forgot now.
Altruists.
Yeah, let's just call them altruists to distinguish from the weaker cooperators. Altruists can be an ESS if omega C is greater than omega D. Do you agree? Okay. So let us now plug all the stuff we have calculated, which means that P of C comma C, B minus C, minus CP D comma C is greater than. Is it fine? I just plugged in the two equations. And let me now put together all the B terms in one side and all the C terms on the other side. Okay. So the B term is this, and C term is this. Okay. So P of C minus P of CD times B must be greater than. There are two C terms. No, they are both negative on the left hand side. When they come to right hand side, they both become positive. C times P of CC plus P of DC. I hope I have made no mistake. Please check the algebra. Is everything fine so far?
Yes.
Yes, sir.
Sure.
Yes.
Yes, sir.
Okay, fine. So now what is the right hand side here? PCC plus PDC. Just think of what each term means. It's the probability of a given cooperator meeting cooperator, right? This term is the probability of a given cooperator meeting the defector or interacting the defector. That means probability of cooperator meeting
1.
either C or D, right? So therefore this has to be equal to 1. Okay. So let us call this left hand side term as capital R. Oh, capital R is something we have used. Let's not call it capital R. Let's call it small r. Okay. So then we have a simplified formula, which is altruist can be an ESS if R times P is greater than C, where R is basically nothing but probability that a given cooperator meets a cooperator minus the probability that a defector can interact with cooperator. Have you all seen this kind of an equation in your life before?
Yeah, it resembles Hamilton's equation, right?
It resembles Hamilton's rule, exactly, yeah. Yeah, absolutely. Except that Hamilton's rules was for a much more specific context. Okay, but this is, in my opinion, a much more general condition. Okay, of when altruists can be an ESS, or at least when altruists can have a higher fitness than defectors. We write that it resembles. Absolutely right. Okay, so just think about what exactly is R. R is basically difference of two interaction probabilities. And what are those two interaction probabilities? The first one is probability of a cooperator finding a cooperator minus probability of a defector finding a cooperator. Okay, so what's the minimum condition that you need for this inequality to be true?
Probability of CC should be greater than CD.
At the very minimum, R must be greater than 0, right? Meaning the probability that cooperators can find cooperators must be higher than the probability of defectors finding a cooperator. That's a very minimum condition. In fact, it must be sufficiently great that R times B must be greater than C. Okay. So how can you achieve this though? What are the different ways of
Spatial segregation?
Absolutely achieve this? There are many ways. Imagine that cooperators and defectors are spatially separated. That's one way. Anything else?
Gatekeeping.
Gatekeeping. Did you say gatekeeping?
Like not allow defectors to
Okay,
enter.
okay, fine, yeah. So somehow, throw defectors out before, before they can come and interact with you, right? Yeah, certainly that's another way. Yeah. So gatekeeping will lead to spatial segregation, doesn't it?
Yes, yes.
Yeah.
Maybe they are temporally segregated. So maybe only
Cooperators are all born together and they
defectors
just okay, yeah, maybe temporal segregation. Yeah. Yeah, that's fine. So basically there are sort of, people sort of classify sort of, the mechanisms by which you can achieve this in sort of, multiple ways. Some people say there are 5 different ways you can do this. Some people say there are maybe they must be merged and called only 2 or 3 types. That depends on researchers' some sort of preference. So broadly speaking, so to keep cooperators out, you're absolutely, spatial segregation. And people say that limited dispersal is often one way you achieve this. If cooperators are dispersing very locally, all of them, that, and if their offspring are also near a parent, then that leads to local segregation of cooperators. Okay. Another one is called behavioral tracking. Now this is a bit stretch from where we began. We assumed that it's a one-time interaction, if you remember, right? So we wrote the payoff matrix for one-time interaction, not for n interactions. But that, keeping that part aside, another way to basically achieve this is behavioral bookkeeping. I don't have to be spatially segregated, but I just keep track of who is doing what. And I will only cooperate with the cooperators, not with the defectors. Okay, that's another way. And another way is basically that of kin, kin interactions. Now, how exactly does kin interactions come into picture is a bit more subtle topic, which I will not probably have time to go through here. But if you read the 3rd chapter of the reference book I have given by McElreath and Boy, it actually starts with this and then helps you navigate through to arrive at what we call Hamilton's rule. Okay, where R basically becomes the relatedness between individuals. Okay, so that's sort of way you actually can maintain altruism, despite the fact that in a well-mixed system or in a system where the random interactions are happening, altruism will not be an ASS. Okay. Any questions on this?
Vishu, I just want to be clear. Is this a one-time process, or iteratively won't the population change over time, or we're for now ignoring that? Like I'm just imagining, like in a very naive case, like B is slightly greater than C, and R is like a number which is greater than 1. So RB is greater than C.
Can R be greater than 1?
Wait, not 1. Okay, okay. R is a reasonably R is positive number, not greater than 1. R is positive number, and RB, this condition is true. I'm just imagining then over time, won't the altruistic things take over, or this is true regardless of how many generations you go forward?
So basically, in every generation, if you want altruists to have a higher fitness than cooperator or the defectors, every generation this must be true. The moment that doesn't happen, the altruist cannot, will begin to lose in the generation. You're right that over generation it's possible that the spatial structure is changing, therefore the R will change. Absolutely, yes, possible.
Like, can they drift towards altruistics being taken over? Because at this instantaneous point of time, if RB is greater than C, yes, altruists will survive. That is clear.
Yeah, but in fact, they will increase more than the defectors. Yeah. So this need not be true forever. Absolutely. Yeah.
That is the part I was not sure of. That's why.
Yes. It's basically this has to be true in every generation. So basically, if you just think of it, how does the entire derivation come, right? So the derivation is for the rate of change of frequencies of a given trait, right? If that has to be positive, we need this to be true, right? If P is the frequency of altruists, for that to increase, omega C has to be greater than omega D, and the moment that flips, P will decrease, right? So you're right. Only as long as this is true, altruists will keep on increasing. Of course, if it is always true and if it reaches 1, they undergo a fixation, then nothing worry. Then everybody is an altruist.
Because I was imagining on the lines of Bayesian mimicry kind of things, how it oscillates around. So it's like
absolutely, it's possible. It's even here it's possible. Yeah, very much. There are cycles of cooperators and defectors that can occur.
Sir, can we have a mixed ESS?
Absolutely, yes. Again, it depends on the way the entire. So basically, depending on how this R depends. Now, R itself could depend on the proportion of altruists and cooperatives. Maybe when altruists are very, very in medium, moderate in numbers, maybe they're able to segregate well from different, defectors, right? But maybe as their numbers increase, it might become difficult for them to segregate.
Stay
In such a
segregated.
case, that means there will be some maximum frequency altruists can maintain while still be to have R be greater than C. Maybe the R will reduce below it, below that minimum value required the moment their numbers are very, very large, right?
Yes, sir. Yeah,
Absolutely, yes, yeah.
Okay.
Okay, so now is this clear now, this point? Okay, now let's now, so the second part that I want to do today is to sort of make connections with some sort of, what am I writing? Billions, I have no idea. Okay. Sort of, some other interesting concepts. So in evolution, broadly in evolution. Okay, now let's go back to this payoff matrix, right? If which strategy, let's again stick to prisoner's dilemma to make our life easy. Now there are two possibilities, right? Everybody is a cooperator in a population. Everybody is a defector. And then of course we have mixed combination. Which of them will have maximum fitness? Which scenario will have maximum fitness? If everybody has, so let's maybe make it more. So let me write down the payoff matrix again. B minus C, B, and 0. Okay. If we have everybody, let's say P's okay. If P is equal to 0, what will be my corresponding population average of fitness? Everybody is now a defector, right?
Yeah, so 0, right?
Huh?
P minus C.
If everybody is a defector,
Sorry, B.
everybody is a defector.
B.
What's the payoff?
0.
0. Only DD interactions happen now. That's basically 0, right? Okay. Let's say P is equal to 1. Okay, which means all altruists. What will be the average fitness?
B minus C.
B minus C. If I assume that B is greater than C, okay, which is a better strategy to adopt for a population?
All altruists,
right?
But not an ESS.
Okay, so assuming B greater than C, P is equal to 1 as maximum population fitness, right? P is equal to 0 as minimum population fitness. But what is the ESS in the well-mixed system?
All defectors.
Is P is equal to 0. So what does this mean? This has an interesting, very simple but interesting consequence. What does it mean? In terms of population fitness?
Yes,
the population is settling for lower benefit than it can, value than it can actually
Yeah, somebody is also saying something. So yeah, any other implications?
What is best for the individual might not be best for the group.
Yeah, right. So what this means is that the evolutionary outcome is determined by not outcome need not be population optimum, right? Right? And is driven by selfish interests. Right? So what matters is whether the individual fitness is increasing while the population fitness may actually be going down. Right? And in fact, individual fitness is increasing just across one generation. It doesn't even bother whether it's increasing across generations. Okay. So this, now let's consider this scenario, a slightly different scenario. Okay. You see there are two populations, population 1 and population 2. Okay. Now we need to let's make it life very easy. So we know that the population 1, let us say, has undergone an ESS and therefore has both defectors. Population 2 hasn't. Therefore, we have just introduced, let's say, cooperators. So now, what will be the payoff of population 1? It will be 0, right? Omega 1 average will be equal to 0. What will be omega 2 average? It will be C. P minus C. Okay. So now imagine the selection is, now there are 4 individuals in this combined population. And in fact, when I say omega 1 average, it's for the population 1. Let's call individuals 1 and 2 here. Let's say omega 1, 1. What was that? That was also 0, right? Omega 1, 2 is also 0. This corresponds to the fitness of these 2 individuals. Likewise, omega 2, 1, what is that? That is B minus C. Omega 2, 2, what is that? B minus C. Okay. Now if you look at these 2 populations as now one bigger population, and then if they all now reproduce proportional to their fitness, what do you think will be the new set of populations? How, hypothetically, how will that look like now?
The P1 should remain same, the number in P1, and CC will increase.
This will remain same, but this will increase. So it depends on, of course, when doing this, we have ignored baseline fitness, right?
Yeah.
Let's assume the baseline fitness for both of them was same. Okay. Okay, and then in such a case, the total fitness of the P2 is higher than that of P1, right? So one possible scenario, as you're saying, is maybe this will not change much. Let's say the baseline fitness was 1. This will remain DD. Okay. If the baseline fitness was 1, okay, this will remain DD. But what will happen to now P2? Let's say that baseline fitness was 1 even here. Let's assume hypothetically that, B minus C is also equal to 1. Just some representative. I have just put some random numbers to make our life a bit easy. So what will this be now?
4 C's.
Okay, there will be now 4 C's because baseline plus the corresponding payoff is now 2. So that means each C is giving rise to 2 individuals, which will have. Okay, is that fine? So now between, let's say if this was the generation T and this was generation T plus 1. Okay, so what was the proportion of cooperators at T? What was that? That was half, right? What was P of T plus 1? It's basically now, what is that? 4 by 6, that is 2 by 3. Oh, sorry. Do you all agree with this? Does it make sense?
Could you please repeat it?
Okay. So in this, let's now go back to this time T, okay, which I'm going to separate with the blue line just to be clear. How many cooperators are there? 2 in P2, right? And 0 in P1. What is the proportion of cooperators if I account for the total population? It's 2 by 4, right? So if P represents proportion of cooperators, what will be PT? It will be 2 by 4, that is half. Is that right?
Yeah, it's clear.
Okay. Now, likewise, if I now do this exactly same thing here, what do we have? 4 by 6, that is 2 by 3. Okay. So, yeah, Bevan, yes.
I'm a bit confused on how the T to T plus 1 transition occurred, like how the reproduction happened.
What part was not clear?
Like in the P2, it became 2 to 4, and
is that clear why it became 2 to 4?
2.
Do you know why it became 2 to 4?
No, like no. That's the.
Do you know why it remained
that's
2
where
to?
I'm stuck.
Do you know why it became 2 to 2 only? Because we assume the baseline fitness was 1. Right? One. What does what fitness of 1 mean? You know, 1 offspring per parent, right?
Okay.
So each parent reproduces 1 offspring. Therefore, I have continued to have DD now. The parents have died.
Okay. Like the parents will die.
Yeah.
Yeah, the parents will die. Okay. Yeah. I got it now.
Now here, likewise, it's omega 0 is the baseline, but B minus C is 1. So fitness per individual is now 2. Okay. So maybe I should write here plus omega 0 plus omega 0. Okay. Therefore, you have 4 C's now. Yes, so basically what has happened is that, so now, what happened? Okay. So if we just revise what we did in this part. So we first said that if we had a single population, over time, what happens? You know, the population will be full of defectors only, right? Because that's the ESS. Okay. Now, what happened in this case? We had 2 populations. Okay. And then what happened? Because of that, at the level of multiple populations, the proportion of cooperators have actually increased. Isn't that right? Okay. So how did that happen? So so to understand that, we need to think of what is called how selection operates. Okay. So okay. So maybe I'll now go to the next slide. So in any given population, defectors are always better than altruists. Do you all agree with this statement? Okay, let's not say better than, always have higher fitness. In any given well-mixed population. Why do you say well-mixed? When a population is well-mixed, the interactions are random. Okay, so in any given population, defectors have always higher fitness than altruists. Do you all agree with this statement? Although I was only showing pairwise interaction so far. Do you agree this is true for even when there are a larger number of individuals?
Yes, sir.
Okay. However, if there are two populations, no, you can also generalize it to multiple populations. Okay. Okay. Let's say P1 has, P1. Okay. Let's say population 1 has P1 proportion of altruists. Let's say this is P2 proportion of altruists. Okay, meaning there's a C, some D's. Okay, C. So I'm just exaggerating a bit here to represent two populations. Okay, so there are P1 and P2. There are now two populations. Okay, which population will have a higher fitness between the two? P1 or P2, the way I have written now?
P2.
Okay, the population 2, the population with higher proportion of altruists, okay, has a higher average fitness. Is that right? Please think about this. So, for example, the population 2 might be one where everybody cooperates, one extreme. But let's say I have put one defector sort of as a mutant here. Okay, so this everybody here has a higher payoff on an average compared to this population that is dominated by defectors. Isn't that right? We all agree with this? Okay, so what you are seeing here is that within population, defectors are always better off in terms of fitness. However, between populations, the population with higher proportion of altruists has a better survival and reproduction possibility, right? Do you see that there is actually a tension, tension sort of, tension between individual, what we call individual level selection, and you can call them two populations or two groups, okay? Or sometimes they're also referred to as Ds, okay? To avoid the confusion, maybe I don't know what is the most, and I'll just use a more general term, into individual selection and demic level. Do you understand that there is actually a tension between some opposing forces sort of happening between the two? Is that point clear? That's the only point I want to make. Huh? And in fact, because of this reason, in the previous example, although defectors have, despite the fact that altruists are at a disadvantage, then proportions were actually increasing in this sort of very simplistic example I gave you, right? Any questions on this? I see massive silence.
So here we are assuming B is greater than C, right?
Say that again.
Over here we are assuming B is
greater than C. Yes, yes, absolutely, yes. Let's stick to that that regime only.
Also, does it assume that cooperators meet cooperators more often here in this?
So we are assuming that each population is well mixed. Okay. So within each population, they are interacting randomly. They're not interacting across populations, but only within populations.
So it's random
within population. Yes, within population. Yes, that's why I said in any given well mixed population. Okay. So within population, I am assuming well mixedness here. Do you see that this is another scenario where the cooperators can still increase? Although within each population, they might be actually decreasing. Do you see that's a possibility?
Sir, but irrespective of the value of P, the eventual outcome is that the population will be filled with Ds, right? Defectors.
Is that always the case, you think?
No, I mean, we have just derived that RB greater than C, then we can have altruists.
Yeah, so one way to achieve that RB greater than C, basically what I'm showing here is some sort of that, spatial segregation phenomenon. If P1 and P2 are sort of segregated, the one dominated by cooperators and one by the defectors, if you maintain that segregation, although within each of these subpopulations, the defectors will always appear to be doing better, but at the total population level, the cooperators will be still doing better. Okay, so now it's actually possible to prove that that is indeed the case. It's not just a verbal argument. It's actually possible to find out that it's actually possible that this situation can happen. So which is where I will leave today. Okay, so what I would like you to do is a very simple exercise, which is we have written this payoff matrix for only two individuals, right? Isn't that right? we have written only for 2 individuals. Do you think you can generalize this to a population? That would be my first question. Can you generalize this to a population? Okay. If there are let's say n1 number of altruists and n2 number of defectors, what is the payoff to altruists and defectors? Okay, so you'll have to make some assumptions to arrive at that, and then you will have to derive the fitness, and then you will have to now find the average fitness for cooperators and defectors across 2 populations, and then calculate when altruists will have a higher fitness. Okay, so now this might be slightly difficult, so what I'm thinking is maybe all that I would like you to do and think today, because I have already covered sufficient number of concepts today which are quite counterintuitive. What I would like you to think and do is, can you generalize this to can you generalize this payoff matrix? Where is it? Okay, third page. Okay, can you generalize this payoff matrix to n individuals in a group or a population? Is it reasonable? Okay, that's the only point I would like you to think. Is that question clear?
Yes, sir.
Sir, but in the derivation of RB greater than C, we already accounted for the proportion of C's and proportion of D's, right? So how is it not a population level estimate?
But the interaction was still pairwise, no?
Okay.
Okay, I mean, okay, so now what does it even mean to say, so maybe one way to, okay, maybe let me rephrase my question. My question is, imagine, so now I have given you this, pairwise payoff matrix, right? Okay, if 2 cooperators meet, what happens? If 2 defectors meet, what happens? If a cooperator and defector meet, I have given you these 4 scenarios in terms of payoff matrix. Now consider a population which has n1 cooperators and n2 defectors. Okay, now let's relax the assumption of one-time interaction. Let's say they don't change the strategy, they just stick to this. But now many such pairwise interactions happen. Okay, so the question I'm asking is, what will be the payoff to cooperators? What will be the payoff to defectors? Is that question clear, Anu? Okay, maybe I'll write this down to make it clear. So consider the population of n1 altruists into effectors. So n is equal to n1 plus n2. Assume repeated pairwise interactions. What will be omega C? What will be omega D? Okay. Now, having done this, so now this will be actually fairly obvious. It just requires you to do what I have done already, right? Now, if we just repeat this process for another population which has, let's say, different n1 and different n2. Okay. And then you can that's when you can actually derive the condition for these two subpopulations where this sort of tension is actually visible. Okay. So anyway, I mean, I think maybe I'm not sure if, since I can't see you and I'm not hearing clear feedback. I don't know, maybe what I'm saying makes sense to you at all or not.
No, so I'm not sure I understand the question. Because when we did the derivation for things like RP greater than C, when we had the proportions, that sort of assuming the average payoff after lots of interactions, right?
It's actually based on probability also, right?
Right,
It's not
right.
necessarily it doesn't have to have many interactions. It's actually based on probability also.
Right. But so here do we consider all possible pairwise interactions since it's finite?
Yes. And then you basically find the average across all of them. Yes.
Right, okay.
I mean, you'll find fairly obvious results for these two, but I would like you to do this very simple exercise. Okay, I think maybe that will clear. If you start doing, maybe I think things might clear up. But I understand that some of you want to go for another meeting. So if you need to leave, please feel free to leave. So those who want to stay can stay on, and I can come back after half an hour and clarify any doubts. Is that fine? Okay. So some of you wanted to leave by, I think, 3:30 or so. So feel free to leave if you like to. So there is no submission required for today. But I hope that by doing this, you will understand some interesting concepts. Okay. So entirely up to you whether you want to stay or whether you want to sort of move on. Entirely up to you. How do others feel like? Do you want to continue or do you want to leave?
I can continue.
Okay. So I will just do the breakout rooms as regularly anyway. Those who would like absolutely can continue, and I'll get back after a short break. I haven't had lunch yet, so I'll have lunch and come back. Breakout rooms, open rooms. Okay. But those who need to can. There's no submission that's necessary to. Okay. I have enabled sharing also.
Hello, anyone? Any problem?
No, sir. I think we're done.
Okay.
Will something more be happening now in 5?
No. Unless you have any questions that I can try to answer.
Oh, okay. No, I don't think so. As of now.
Okay, sounds good.
Actually, I do have a question.
Yeah, please tell me.
So, we did this, what you had asked us to do, and arrived at a measure for population fitness, assuming all interactions. And this term.
Not the population fitness. I wanted to calculate the fitness of two strategies.
Right, yeah, and then population, because once you calculate the fitness of both strategies, we try to calculate the average fitness to see if you can show that if you have more cooperators, there is more fitness in the whole population.
Okay.
And we are getting that, but there's also a dependence on population size, and I don't know if that's significant. It's
So,
not intuitive to me.
yeah, it's actually a bit tricky. Maybe I don't know if I will have time to cover that part. But people are interested, I can do that. But today I didn't want to push too much because of that, incident that happened 2 days ago.
Right.
I didn't want to insist on a complicated assignment. I just wanted to get a few things done. Okay. But maybe I can just because next week I want to move on to a new topic. So I don't know if I will continue this again next week. But I will. Sorry, if people are still interested, I can try to actually cover that, what is that, tensions between what's called levels of selections. Okay. Yeah, I haven't seen your most recent email actually. I haven't read them carefully enough. I understand. I think the